Today, our AUC Data Science Seminar Series features Dr. Stephon Alexander, who will talk to us about data, physics, and jazz. Dr. Alexander is a musician and professor of physics and astronomy at Brown University, that's in Providence, Rhode Island. He was born in Trinidad and is a theoretical physicist, jazz saxophonist, and author specializing in the interface between cosmology, particle physics, and quantum theory. He is also the past president of the National Society of Black Physicists. He was recently recognized for his contributions to understanding the potential quantum mechanical origins of the cosmological constant and for exploring consequences and observational signatures of fundamental symmetry violations in the gravitational sector by the American Physical Society, where he is now a fellow. Huge honor. So congrats on that feat. Dr. Alexander has worked on a variety of projects throughout his career. In August of 2014, he released a critically acclaimed album, Here Comes Now, in collaboration with the electronic producer Ryux. His 2016 book, The Jazz of Physics, explores the link between music and the structure of the universe. At Brown University, Dr. Alexander is also a professor in their STEM Jazz organization. STEM Jazz was founded back in 2018 to be an incubator and networking hub that explores areas of intersections and commonalities between researchers across STEM fields and their distinct disciplinary focus. So we are super excited to have Dr. Alexander here, who is highly accomplished and super amazing. And I am going to stop sharing my screen so he can share his and also his phenomenal insights and work. So Dr. Alexander, welcome to the A virtually. Super excited to have you here.
Yeah, thank you so much, Dr. Washington, or as we kindly know you as Talitha. Well, it's a special honor, and I can't, the introduction just made me blush, but unfortunately you can't really see it. So let me, so it's a real honor to be with you all today. Wish I could be in beautiful Atlanta, one of my favorite cities in the US. I love me some Buckhead every time now and then, some good ribs. But we can, when I come out there in person, maybe I can be treated to that. So on that note, let's begin. So my title is Data, Physics, and Jazz, and you probably wonder, what does, we can understand what data and physics are related, but what does this have to do with jazz? And I guess my message, my overarching message, is that I find that, as an African-American man in the United States, a big part of one of the greatest achievements that came from the United States, both artistic and intellectual achievements, is jazz music created by our community. And I found that, by sort of not, throughout my journey, not separating sort of those aspects of myself, meaning my involvement with music, my involvement with my culture and jazz, especially, into my research, my exploration, my scholarship, that basically allowing those worlds and embracing those worlds to speak to each other, that it does lead to new insight. And I think we are, and that's why I think what's so special and unique about AUC is this potential, and the fact that y'all, and with the leadership of Dr. Washington, are actually embracing. I think this is where we're gonna have both low-hanging fruits as well as what we call hidden advantages. So let's begin with this. This is more of a story of unlikely sets of discoveries, unlikely connections that have been made. And this is, part of a many-faceted narrative. So let's begin. When I was a kid, I grew up in the Bronx, New York. There's something I need to, I can't see my slide. There's something that came up here. Okay, now I can see my slide. So, as a kid, growing up in the Bronx, New York, I came from a musical family, and I was also very inquisitive. And at that time, there really weren't any, many Black scientists, and this was in the 80s, as much as we have today, that were acting as role models. So I kind of sought that out in the musicians. What do I mean by that? When in the Bronx during the 80s, hip hop was something that was blossoming in the Bronx. And, we have like Rakim, who still is around today, who's still prominent in the hip hop world. But back then he was known to be one of the most definitely popular and famous and skilled MCs. And back then, rappers were making allusions and connections to scientific concepts. They sometimes call it dropping science or going back to the lab or supreme mathematics. So this is one of his lyrics here. That's what I'm saying. I drop science like a scientist. My melodies are cold the very next episode. Has a mic off in the store and ready to explode. I keep the mic at Fahrenheit, freeze MCs to make them colder. The listener's system is kicking like solar. So Rakim is making an allusion to a supernova explosion, and he's comparing, he is likening his rhyme delivery to that of the most significant explosion that a galaxy can experience. And this is the kind of stuff that, when you have a very famous rapper, nerding out like that, it kind of made it okay for a young 14-year-old kid to kind of embrace his inner nerd. As I started to, let me just say that, this scientist versus a musician thing as a teenager, this is a very common thing for a lot of young people. Should I pursue something that fits more into the stereotype of what's expected of us? Or should I try to pursue my real interest maybe, but it may not, maybe there are not a lot of us doing that kind of stuff. And it's not expected for us to do well in those things. That was a similar tension that I was experiencing. And the way I was able to, resolve that or integrate that or navigate that was to find that there were other great scientists and musicians who did crosstalk, who embraced science and who embraced music. Another person was Albert Einstein. We know him for being, one of the greatest physicists, probably the greatest physicist of all history, but he played his violin and he would improvise on his piano when he got stuck on physics problems. And he very much wore his personality on his sleeve. He wasn't your stereotypical, geek, hide in the basement that's impersonable. He was very human in a lot of ways. And he was also a civil rights activist. He was friends with Paul Robeson, for example, and W.B. Du Bois. And another person that played a major role was my first PhD advisor, Leon Cooper, who was a fellow New Yorker. And Leon won the Nobel Prize in physics at a very young age for superconductivity, which plays a big role in our semiconductor technology. But he moved on from them. He reinvented himself. He showed that you don't have to get stuck in a one-track lane, and he moved actually into machine learning. So he was one of the early people, a physicist, that moved into machine learning. And then what happened was I started life off working in that field in the 90s, but then of course I transitioned out of that into cosmology. And Leon and I, most of our time would be spent before I became a student talking in the elevator about speakers and which is the best speaker to buy, and he was really into music, right? So again, finding like-minded souls is also a very important thing, and we're out there. And of course, probably most importantly, John Coltrane. John Coltrane, known probably to be one of the greatest American composers of any genre of music. But Coltrane didn't stop there. See, Coltrane basically was a frustrated mathematician. Back then, African Americans in the 60s, we weren't really allowed to go to places like MIT and these places, right? And I've come to the conclusion by talking to many people that knew Coltrane, including his son, Ravi Coltrane, that he basically, really loved mathematics and Albert Einstein. And what we're looking at here is a hand-drawn diagram where he's exploring the system that Albert Einstein used for physics, which has to do with symmetries, and applying it to his own musical system. And, you know, this is Coltrane self-teaching himself, right? So he not only was, you know, did all this amazing stuff in jazz music, and as a musician, as a composer, but he also embraced mathematics as well. So, you know, what I want to kind of take us through is actually this connection between music, mathematics, and physics. Actually, there was a time at the very birth, at least in the West. I mean, this was certainly the case in like Egypt, where the birth of what we call mathematics and physics and music were actually one. It was only until later on that they bifurcated. And this kind of began with Pythagoras. Pythagoras believed, you know, of course, he came up with the Pythagorean theorem, a squared plus b squared equals c squared, and the Pythagorean system in Greek philosophy, which basically developed mathematical proofs and geometry as a way to investigate the universe and investigate physics. But he also believed, weirdly, that the planets played a harmony as they moved around the Earth. Back then, we lived in an Earth-centric universe. And he called it harmony of the spheres. And to convince himself that this was true, so the idea was that the planets, right, were separated from each other by whole integer ratios. And they played a harmony. So to demonstrate this, he built an instrument and divided, basically, as you see, a string into half integer or into integer divisions of the original length of the string. And lo and behold, he discovered what we call the Western musical scale. Do, re, mi, fa, sol, la, ti, do. That is basically what we call a harmonic series. And that was discovered by Pythagoras because he believed that the planets were doing this. Now, that's a bit weird when you think about it. But, you know, about 2,000 years later, in really trying to understand the motion of planets and trying to write down the first sets of equations, now known as Kepler's law, Kepler revisited Pythagoras' idea. And before figuring out this ingenious leap to find out the motions of the planet, Kepler basically realized that if he wrote down the notes associated with the speed of the planets, like what Pythagoras was imagining, by taking the ratios of the planets, here is his own handwriting, where you can see him writing all those notes. He was able to then come up with the first sets of equations called Kepler's laws, which are based on the mathematics of an ellipse. And up till today, we still use this mathematics and these equations to discover exoplanets. So you see, there's been a long tradition of how music is connected to physics and astrophysics. So we can ask ourselves today, we know that now there are trillions of planets, even in our own galaxy. And there are yet billions of galaxies out there. Does the universe now have a musical character? So I want to talk a little bit about that. But before we do that, let's delve into a little bit of background, some common language that we're going to use. And this has to do with how waves add and subtract. So if you look at these two waves here, like think about them as sound waves, right? So that's what your noise canceling headphones may do. It will basically, if it wants to cancel a noise, it'll pick up the noise and create an anti-wave that's exactly opposite. And then that will cancel, that will interact with the noise, and then it will cancel away the noise. So how does this happen? Well, if you see two waves that are exactly on top of each other, and when they add up, I create a bigger wave. But if I have two waves that are sort of opposite each other, meaning that where it's high, the other wave is lowest, and vice versa, to the right there, then those waves will cancel out and they will subtract. That's called destructive interference, and the other one's called constructive, meaning it constructively interferes to make two smaller waves bigger. And we can understand a lot of how instruments work, or basically these types of waves that can be added up together to create interesting sounds, right? So what we're looking at here is that if I look at three perfectly periodic waves and I add them up together, I get, as a result, a more complicated looking wave. And this is at the heart of a lot of signal processing and machine learning, actually. where we can take a lot of, we can take a lot of signals, convolve them, bring them together, right? And create more interesting patterns, or we can take a very complicated pattern and decompose it into simple digital bits of information. And this is also at the heart of how musical instruments actually work. So now what I want to do now is show you some interesting data of the distribution of something called dark matter and galaxies in our universe. So what I first need to do is tell you that our universe has been expanded. We have observed that effect. So on the largest scales, when we look at galaxies and we see them all rushing away from each other, which is a sign of expansion. This movie is supposed to give us a feeling of like at the Big Bang, when the universe had no galaxies, and as it expanded and cooled, and the matter and energy basically condensed to form galaxies, and then galaxies eventually form. What we can see here is the Big Bang, boom, and then first light, we see the formation of galaxies, and the galaxies are expanding away. And one of the jobs we want to do in cosmology, is still very much active research, is to understand when we point our telescope, we can measure billions of galaxies and basically take a picture, a snapshot of the patterns in the spatial organization of galaxies. And we'd like to learn, just the way like we want to do an image detection. For example, if I see a cat or a dog, I could train a neural network, right? To learn basically and internalize that when I see a cat, there's a cat, I see a dog, there's a dog. And then it'll be able to, if I give you a new image, whether this thing is to classify whether it's a cat or a dog or something else. We would like to do a same thing here in cosmology. What we'd like to do is to look at the patterns of these galaxies and infer from that picture something about the laws of physics based on those images. And I'll get back to that in a second. So what we're looking at here is a large-scale distribution of what we call the cosmic web. If you look at this image, you'll see like a web-like or sort of wave-like structure of the light. If you zoom in, as we're doing here, and you continue to zoom in, that little bright spot there corresponds to what we call a dark cluster of something called dark matter. I'll tell you more about dark matter in a second. So we see this pattern of dark matter, and that's actually where galaxies, like our own Milky Way, will reside. And by understanding these patterns, we are able to understand something about what the nature of this dark matter is, how it formed, how the laws of physics actually operated. So we're trying to do inference, basically, and infer the laws of physics by looking at this visual pattern. This is one of the things that big data and machine learning is useful for. Inferring useful information by looking at complicated or mysterious looking pictures. What we're looking at here, so this is the universe about 13 billion years after the Big Bang. And this is a picture of the universe about, 300,000 years after the Big Bang, where it's basically, the way you should imagine this is that back then there were no galaxies. The universe was like a seething ocean of energy and subatomic particles. And what you're looking at here, these different colorations correspond to waves. And the energy, the basic physical picture here is that the energy in these waves, right? That energy basically contains the information, or contains basically the energy in those waves are the things that will eventually condense and collapse to form the first stars, which then become the first galaxies. And I want to show you a really interesting picture of how all of this connects up with music. This is a picture of how this early universe can develop from then to the large-scale structure, the cosmic web. This is a computer simulation of that. And to understand, let's go back to our picture of the instrument. So we learned that an instrument, when it plays a note, it creates a wave pattern in the instrument. And every wave corresponds to a different note, a different tone. The higher the frequency of the wave, the higher the tone. The lower, the less ripples in the waves, the lower the note. But actually, that's not what really happens in a real instrument. In a real instrument, if I play one note, say in this flute here, one note, what's really going on is that the instrument generates a whole range of different frequencies. So the x-axis corresponds to a range of different frequencies. And what we see is that when this instrument plays one note, the y-axis is the loudest, is where the note is the loudest. The loudest, the highest peak there is the note that you actually hear. But the other peaks reveal the material, the vibrational patterns of the instrument. So it tells you the information about the shape and the geometry of the instrument, as well as its material makeup. So that's why a metallic instrument like a flute sounds different than a wooden instrument like a clarinet. Its vibration reveals the material, whether it's made up of wood or metal. And that's what this more complicated spectra or range of frequencies is doing. So if we look now, if we ask ourselves a question, what did the wave patterns of the early universe look like? Lo and behold, and the Nobel Prize was given for this. This looks very chaotic. It turns out it actually looks like this. It behaves like an instrument. So the early universe, with this seething with this vibrational pattern, is actually generating sound waves. And it's those sound waves that become the first stars in galaxies. Now I want to end with talking about some recent research that my research group is involved in. And as I said, when we look at this large-scale structure, in the regions where you see all these things coming into this region here, that is a region where there's this thing called dark matter. And we don't know what dark matter is. It's a complete mystery, but we can measure the effects of dark matter. Dark matter is basically the following thing. One way to think about this, it's sort of like a cosmic silly putty. It wants the visible matter. It's a way of gluing the visible matter to it, right? So why is it doing that? Well, first of all, it's a mysterious, invisible form of matter. So it's invisible, but it has weight. And because it has weight, it basically can speed up or expedite the process of forming stars and galaxies. So if dark matter did not exist, we would not exist, right? So I like to call dark matter black power, right? So the idea here is that without this invisible matter, galaxies and stars would not have enough time in cosmic history to form. And without stars, we'd have no planets, we'd not have us. So we need the dark matter. But what is the dark matter? So let me show you a nice little picture here. So to the right, you see, if you look at the center, that's supposed to be a picture of a spiral galaxy. Think of that as like a frisbee. And the frisbee is made up of a whole bunch of stars, and it's spinning around a common center. We now know that that common center contains a supermassive black hole at the center of our galaxy. And the point here is that when we measure how fast the galaxy is moving, we find that the galaxy is moving way too fast for the amount of mass contained in it. What do I mean by this is that if I count, we know that if I take like the sun and I have the earth, the heavier the sun is, the faster the earth will move around the sun, right? And the smaller, the less the sun weighs, the slower the earth will move around. Likewise, a galaxy is made up of a whole bunch of stars, and they're moving around the common center. And the more mass contained in the galaxy, the faster the stars will move. And what we see is that our sun, for example, is moving way too fast for the amount of mass that we can have, visible matter that we can account for. And in fact, 85% of that matter that's accounted for the speed of the galaxy is missing. And that's how we know that there's dark matter in the galaxy. And we believe that the dark matter, this invisible matter, surrounds our galaxy like a spherical sort of ball. We call it a dark halo. So there's the picture you should have here is that you have like our galaxy spinning around, and then enclosing it is this dark matter cloud that's spherically symmetric. And if you have this dark matter, it will account for the motion of galaxies. But what is it? Well, there are tons of theories on the market, right? And part of what we need to do is to figure out how to see in the dark. So one way we can do this is through the phenomenon that Albert Einstein came up with. See, Einstein tells you that if something has a lot of mass, it will warp space. So what we're looking at here, if you look at the picture to the top there, you'll see that there's a galaxy. That's supposed to be a galaxy that we're watching with our telescope. And if in between the galaxy and us, there's some dark matter, it will actually warp space like a lens. And instead of seeing the galaxy the same way like a kaleidoscope lens will make an image distorted, what we will see is what we call a gravitationally lensed image. And the image at the bottom is actually a real image taken by a telescope of a lensing effect. So that little area around is really one galaxy that gets warped due to the gravitational lensing. And so if dark matter exists, right, we will be able to see this effect, and we do see the effect of dark matter actually this way. So here's the idea. And here's where the data, the big data part of my talk comes in, to my music and my physics. You see, there are special classes of dark matter models that predict something called vortices. So there are lots of dark matter models on the market. We would like to distinguish between them and say, okay, this is not the dark matter. This is closer to the dark matter. And the type of dark matter, the ones that have a lot of, they're very well motivated by our modern theories of physics, admit what we call structures. So I want you to think about this dark matter as some sort of like invisible fluid. And imagine that this fluid could rotate. And if it rotates, I want you to think about water going down the sink. What happens when if you have a sink that's really full and there's water going down the sink? Well, you see that there's going to be a little hole at the center, like a line-like hole, right? That's actually an example of a vortex. Or the eye of a storm, of a hurricane. That spin in local region is actually an example of a vortex. And there are very well motivated models of dark matter that actually admit these types of line-like structures that can be living in a galaxy. And so because of that, that means that they can have concentrated regions of extra matter, and that could actually affect a gravitational lens. So if I have now a vortex on top of my dark matter, living a whole bunch of them living in there, you know, it will distort, it will change the gravitational lens. And so a big, over the years, my research group have taken on, we have basically applied using the same way we can use, you know, convoluted neural networks to do image detection and classification. What we want to do is do image classification of these gravitational lenses. So the idea is that we will take images of the gravitational lenses that we get from the LSST, these surveys that will take pictures of these gravitational lenses. Then we will train our neural network to be sensitive to these vortex-like defects. And then we will look at, the idea is that we will train our neural networks to be sensitive to detecting these types of, these vortices, then look at real data and deduce whether or not the real data actually has these vortices. So how does that work? So let me show you an example of if I had a vortex substructure, so the substructure means that we have a dark matter halo, that's like good old-fashioned dark matter, how it should exist. And then there's maybe a vortex, and imagine that it's 1% a tiny 1%, all right? What you'll see in the image is that it can change the image, how the image is lensed, how the light bends, in very distinct ways. And by using a CNN, convolutional neural network, we can train the neural network to actually to be able to, you see, our naked eyes cannot see the difference. If 1% of a galaxy, of an entire galaxy, hosts 1% of it, hosts a vortex, the naked eye can't do it. But it turns out what we found is that a neural network and machine learning could detect it. And in fact, what we find is that we can simulate the effects of the substructure, right, in a CNN and get a near perfect classification. In other words, it's able to find whether or not the galaxy will have a vortex or not, even if the difference is 1%. And so what we're looking at here is some preliminary data. And so moving forward, what we want to do now is that for future, when we get more data, right now we don't have a lot of data, but as we get more data, and we expect to get thousands of these lensing images, we will be prepared. We would have the tools to be able to distinguish between different classes of dark matter models by looking at these very faint and invisible, seen in the dark. So the idea here is that we can use now learning, deep learning, to actually see in the dark. And that concludes my talk. And I hope that you see that by my journey, but by just looking at the ways the music and the ideas in music can be connected to my physics, basically led me down this rabbit hole. And I really encourage and inspire you all to embrace your full selves as the AUC takes it to the next level. Thank you for your time.
And thank you so much, Dr. Alexander. That was amazing. And as you can see from the chat, I think our audience definitely does agree. Somebody said, this is so beautiful. Artistically, it looks like neural network in the brain. So people have really loved your presentation. And you can stop sharing your screen now if you'd like. So you can take a break there.
Good.
And
there we go.
There it goes. And while people are putting some questions in the Q&A, I am going to read out the poll results here for who's joining us today. So the first question is, what is your status? So 19% or 13 are currently enrolled students, those who responded. Not everybody did, but it's all good. They're probably enthralled by your presentation. And so 81% or 55 said they graduated or they're working professional. We have a freshman, a couple sophomores, a senior, 4 masters, 9 PhD students, and others who are not currently enrolled students, but we're all lifelong learners. For the gender balance, it's kind of split, 56% or 38 female, 43% or 29 male, and 1 other. And where do you currently live? So 33 say they're in Georgia, and 35 are not in Georgia. If you'd like to put where you're from in the chat, feel free to do so. And by the way, I'm coming to you from Midtown Atlanta. So there's a question, a trivia question here. John Coltrane composed which one of these songs? Was it a coal train? Was it a blue train? Was it the midnight train to Georgia? Was it a love train?
Wait, is that question for me or for everybody?
Yeah, that's for everybody.
Okay, good.
And now I'm going to pitch it to you.
Yes, I know the answer, of course.
All right, go ahead. Tell us the answer, and we'll look to see who won.
Blue train.
Blue train, yes. So 40 or 59% selected blue train. It was not the midnight train to Georgia, but next time you're on Amtrak, Dr. Alexander, you can head on south, right? And so we asked the question, which note is not on the pentatonic scale? Is it A, B, C, D, or G? Dr. Alexander. Which one's not on the pentatonic scale?
Well, it depends on which one, but for me, it will be B.
It would be B. And it looks like the majority of the respondents agree with you, and that is the right answer. So it is B, so 20 or 29%. Fantastic. So good job, everybody. Thanks for participating in our poll today. Somebody said they were thinking E minor. What can you do? Oh, no. So, okay, great. So I'm going to dive into the questions here. And so somebody said, is it possible for a low tone to also be of high frequency?
The answer is there are, I think there's a psychological or neurological, a phenomenon in the brain. I think it's called ghost notes or something. Maybe I missed it. But the idea is that while you're playing a given note, your brain actually perceives it as a different note or a higher pitch. Or sometimes will fill in, the information that's not actually physically present. So that's an example. I don't know if it's exactly this question, but our brains have a way of actually hearing different things that's actually being played.
Wonderful.
And a lot of hip hop geniuses, for example, like Jay Dilla and a lot of people people, their genius was actually, they would make rhythms and beats that would actually make things sound different or faster or slower. That was part of their genius, actually.
Awesome. Awesome. Thank you. So someone says, so does the dark matter vortices create the phenomenon of portals? And is this physics concept also similar to sinkholes?
Okay. Yes. I mean, this idea of a vortex is a very generic physical phenomenon that plays itself out in all these different, subfields. And Dr. Washington knows that you find these solutions a lot in differential equations, right? PDEs, things like that.
Yeah, I love a good PDE. All things nonlinear.
That's right. Well, very good. It's a nonlinear phenomenon. Thank you.
So somebody says, in the past, physics teachers in K-12 have not been as open to jazz and vice versa. How can we encourage teachers to be more interdisciplinary?
Get them to come to the AUC talks. I'm actually serious. I think having teachers exposed to wider audiences like of this nature is a way of doing this kind of things. I mean, one thing I've done is I go and I visit schools sometime whenever I have time, and I engage with students and teachers.
Great. Yeah. And we have people all the way from California on the webinar, so it's open. And I know here in the AUC, our Deputy Director, Dr. Justin Ballinger, he's standing up an AUC Data Science for K-12 working group, and they're doing some phenomenal work. So stay tuned for that. And by the way, thank you, Dr. Nutrice Gassens, for the question. And I'm sure Dr. Alexander will look for your imagery. I'll share that with you later, Stephon.
Yes, please.
Yeah. So someone asked, any plans to use the new JWST images for your analysis?
If I get access to it, I mean, but I would say that it depends. It depends on if the nature of the questions that I'm asking would be relevant. But at the moment, maybe not yet. But you never know.
Never say never. Someone asked if you could define CNN again, just one more time.
Yes. By a CNN, I mean a convoluted neural network, and all that really means is that you have some kind of image, or that's you're trying to learn a function, right? Y to X, but and you use matrices or the convolution of matrices to look for those patterns. And so when you convolve matrices, it can pick out similarities for different patterns. So that's a basic idea there. And it's just a nice Y is equal to AX, right, plus B, where Y and X are matrices.
You got it. So you can just think of the matrix as a function of sorts.
That's right, exactly.
Linear array.
A linear array.
One from the other. So when things get convoluted, perhaps that can help unpack.
That's right. Right. And at the heart of that, actually, the unpacking, remember I used this idea of these waves. Well, even these waves can actually be represented in some interesting ways. You can map those to actually those functions and the deconvolution. Think about deconvolving into all these different wave patterns as one representation of that.
Yeah.
To take your idea further.
Yeah, because usually, when we're growing up, we're given a function, we do some stuff with it. But then once we're grown up, I don't know, we're given the stuff around the function, and then we have to find out what that function is that could either uncover or map one thing to another in some sort of way or phenomenon. So it's finding that function element, which could be like a matrix or something. And that's the creativity. That's the fun part, right?
That's the fun part. It's a detective work, right?
It is. It is. I say as an applied mathematician, which, interplays nicely with physics, it is detective work.
You guys are basically physicists in my book, so.
Well, you say physicist or mathematician. It's all good, but it's all data.
Well, it's all chitlins.
There it is. Okay. Someone said, would you recommend any journals which talk about music and mathematics, or music and data, or music and jazz? Are there any journals around these intersections?
Yeah. Well, I don't know if right now there is, as you know, we use a lot of, like, I don't want to name any companies but there are some companies that part of their job is to listen to music and determine what song you're listening to or things like that, right? And that basically is a use of machine learning, as you know, to be able to classify what song you're hearing. There are some things that I'm sure we all have on our phone. It's one of my favorite apps, starts with an S, that could do that. So there is a program that I'm affiliated with at NYU called a music tech program. And a big part of what they do is use machine learning to, to answer all sorts of questions about music. And one of the things that people would love to do is to teach a machine, right, how to improvise. But in terms of journals, there's nothing on the top of my head that's coming up. But if you look at this center, I'm sure you'll be able to find, so there's a journal of music and mathematics, for example, and that's a place where you'll see a lot of this kind of work coming through.
Yeah. Fantastic. And I put a link to AMS just for, so it's not a journal, but now some videos there of other folks like Dave Kahn, who also does the intersection of music and math. Right. And I also put a link to the STEM Jazz at Brown group too. Do you want to talk a little bit about what is the STEM Jazz at Brown? What do y'all do? Yeah,
it's it's a collective of graduate students, postdocs, and faculty of color at Brown University in STEM, all ranging the entire breadth of all the different STEM fields, mathematics, physics, chemistry, biology, computer science, neuroscience, right? The whole gamut. And we basically, get together kind of informally actually, and kick it and talk about very informally our work. And the idea is that we hope to cross-pollinate, research and, amongst each other. And it's already, I think we have on the order of like, say, 50 members. So it's actually a significant number of people. And it's, I think, quite unique, especially for like a predominantly white institution like Brown. It's a very unique thing. So, and a lot of fun. So y'all should come visit. Yeah, I need to come visit. One of our students. You are invited, but you have to come at a level at a presidential level for that.
All right, well, let me know. We have a Clark Atlanta student, the master's in data science program there. So I told her I would come and check on her. So I got to do my job.
We'll make that happen. That's easy.
All right.
That's all hanging fruit.
Oh, fantastic. Someone said, I found that parametric design is key in improving machine learning's predictability. Am I correct in hearing you that the people who embrace their creative minds are able to find more precise solutions?
Wait, say the last part of the question.
So they said that you had mentioned that the people who embrace their creative minds
Yes.
are able to find more precise solutions.
Well, it's been my experience that is the case. You know, why leave any stone unturned? And if, like, you know, you have other creative access to your process, whatever that may be, including music or dance or, you know, yoga, whatever those things are, you know, I think it's to not cut those things off, because you never know where the inspiration, where the connection will happen.
Yeah, I find my creative mind goes usually in the middle of kickboxing class.
Oh, okay. Just don't kick too creatively.
I have an idea. You know, a couple hours later, it may or may not be a good idea.
Right. That's a good one.
Cool, thanks. So drawing comparisons between sound and light and recognizing dark matter, are you saying that the two behave in the same way?
Well, that's a really good insight that this question made. I didn't think about it quite that way, but you know, we are basically seeing, I mean, the dark matter is made, it is some type of fluid that can undergo vibrations, but we can infer the dark by looking at how light is bent around it. So they're connected in that way. Let me think about that. It's a good question.
All right, think about it. That's good. Someone asked, how can music be used to understand atomic structure or bonding?
Well, you know, in quantum physics, we learned that basically when we look at that basically the atomic orbits are wave patterns. Actually, they're literally wave patterns of a linear differential equation called a Schrodinger equation. So you have these wave patterns, and it turns out actually that some bonding actually has to do with resonances in these waves. So therefore, and remember, a sound, you know, a given note versus another note are different resonances actually. So it's in that sense you can think of where you have constructive interference or resonance, you can have bonding. Where you don't, you have anti-bonding. So it's in that sense the analogy goes through.
Awesome. Someone asked if you're going to play your jazz for us today, because they sure would love to hear some music.
Well, I did not bring my horn as I was trying. I did travel, and I did not bring her. But you can find right now, as you wish, online. You know, one of my solos. So you can literally find something online.
Yeah, I just put a link in the chat where you were on the beautiful relationship between physics and jazz with the Wired.
Yeah, that's an example of me playing. That's actually a complete improvisation.
Do you want me to play like a 30-second clip?
Yeah, sure, yeah.
Okay, I mean, I
yes,
just
they literally, when I was at Y, they said pick your horn and just play it. And I was like, why? And they recorded it.
Okay, so I'm going to do it a prop to play here. Here we go.
I find that both conceptually and in terms of style, that there are lots of interesting parallels between
I'm picking up the sax.
Jazz improvisation and how theoretical physicists, which is what I do for a living, how we actually come up with new ideas, come up with new physics. So one connection is the mysterious way that quantum particles actually.
All right, so what I'm going to do, I'm going to leave that for our viewers to go and check
listen to themselves. Yeah.
Yes, were you able to hear it okay?
I couldn't hear the music because I think the way the thing worked, it only picked my voice out. It filtered out the music. So
all right, well, everybody, so check out the link in the YouTube. It's about a minute clip But check them out. You'll hear some playing there. And you know, we got to bring you down to the A sometime and do a jazz session with you.
I'm always up for that. There's some great musicians in Atlanta, so I would love to come down and swing it with some people.
Yeah, we have some fantastic jazz ensembles at the schools here.
Good. Well, I'm happy to play with them.
Oh yeah, we got to make
As
that.
long as they don't make me look like a fool, but you know, I'm just kidding.
You know, we do have AUC excellence, so you better watch out.
I know. I'm always overshadowed by the excellence, AC excellence, you know.
No, we open our doors for everyone, you know. Yeah, everyone's invited.
You know, the Northerners here, the Yankees.
Yeah, we take everybody. Yesterday we had the director of the U.S. Census here, and Prairie View A&M was in town. And we said, come on down and hang out with us. Yeah, so yeah, our doors are open. That's for everybody on the call. If you ever want to come hang out and do data with us, just come on by. You know,
Data is dope. I like that. Data is dope. I got to get that T-shirt.
You got to let us know your size and we'll hook you up.
Large.
Okay, we'll get that. Fantastic. So I think we have time for one more question. A good old Fourier transform. Everybody loves good old Fourier transform. Is definitely amazing. And we have only scratched its surface. What do you think about more applications in music?
Well, I mean, you know, it started life off, you know, that's a good question. What are, you know, I think one place is actually, yeah, in improvisation. And basically, if I think of like a random distribution of Fourier transform, and you know, and as you know, the Fourier transform can pick out certain notes, right, in a spectrum of sound. And you know, it might be a fun thing, a fun thing to experiment with. So I think this will be something that one can experiment with, right, play with, and see, you know, see what it gives you. So I'll leave it at that.
Fantastic. Well, Dr. Alexander, this has been super fun. Thanks, Bettina, putting the link in the chat for some Fourier transform and music in there. We hope, you know, as a former member, current member, paid member of the Morehouse Marching Maroon Tigers, also known as the House of Funk, and director of the AUC Data Science Initiative, I thank you for coming and sharing some data, physics, and jazz with us on this fantastic Veterans Day. We really enjoyed your presentation, and don't worry, everybody, you'll be able to find it on YouTube, and it's already on Facebook, so you can go there and watch it now. It'll be on YouTube coming up next week. This concludes our seminar series for the fall semester. We'll be back on the 4th Friday in January for some sports and data. So come back with us. We'll have some special guests there. So watch out. And I think there's some people on this call who will be receiving an invite that haven't received it yet. You know who you are. Anyway, so thanks again, Dr. Alexander, for joining us. Thanks, everybody. Hope you have a great rest of your weekend, great rest of your year. Come hang out, do data with us, check out our newsletter, stay engaged, stay connected, and stay curious. Have a great rest of your day. Thanks, Dr. Alexander.
Thank you. See you soon.
See you soon.